All right, we are here at section 4.3, which is curve sketching. So I feel like I keep talking about this all the time about like how eventually like this is where we're going to end up with all these derivatives. And now here we are. So the whole idea of us really learning how to take derivatives is so that we can apply them to other types of problems. And curve sketching is something that we can get a fuller picture of by just being able to take derivatives. So you learned how to graph, for instance, rational functions and polynomial functions and radical functions back in college algebra, but there was a lot you couldn't do without derivatives. Now that we know something about maximum values and minimum values and concave down and concave up, we can get a much fuller picture of the graph than we could have by just plotting points and looking at X and Y intercepts and turning points. Although we are going to still use some of those concepts from college algebra. I'm not going to be focusing so much about like turning points of functions. If you remember that from college algebra, though, and you want to use it, that's fine. I will be talking about using X and Y intercepts and talking about the domain of a function and combining all these algebraic topics with our derivatives. So I love this section. It's one of my favorite things to do. So I'm really, really excited. The coolest thing is when you get done with this, you get to put the function in your calculator to check it. And hopefully you get the same picture in your calculator that you graph using the information you gained mathematically. It's a very rewarding feeling. It really is. All right, so recall asymptotes of rational functions. We have two different types. One of them is a vertical asymptote. We're going to set d of x, which in this case is your denominator, equal to 0 and solve. Now, this is provided the x values obtained do not also make the numerator 0. 0 over 0 is indeterminate. It does not give you a horizontal asymptote or a vertical asymptote. Or horizontal asymptote, I meant to say vertical. So we're setting the denominator equal to 0 and solving for values of x. That's how we get vertical asymptotes. We were talking about that, though, already in the last section. Oh yeah, we were doing that. We were talking about evaluating these derivatives and doing sign analysis. All right, now horizontal asymptotes have three cases. I reminded you of how to do this back when we were talking about limits at infinity, and I reminded you of these rules. So when we're talking about limits at infinity, we're really talking about horizontal asymptotes. So what happens to the behavior of the graph as x gets incredibly large heading towards infinity, or as x gets incredibly small heading towards negative infinity. So the cases will be if the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is y equals 0. And the degrees are the same in the numerator and denominator, and y equals the ratio of the leading coefficients is going to be the equation for your vertical asymptote. And again, this is all stuff that we did back in chapter 2 when we were talking about limits and infinity. Slant asymptotes are going to occur if the degree of the numerator is equal to the degree of the denominator plus 1. So it's always, the degree of the numerator will always be 1 more than the degree of the denominator. So it's a very special case. We don't often have them, but we could have them. To find a slant asymptote, we perform a long division on the rational expression. And the equation of the slant asymptote is y equals whatever that quotient is. So we may or may not actually get to talking about slant asymptotes. We'll see. Okay. But they do technically exist. All right. The first thing we're going to do here. Oh, I forgot to mention intercepts. This is incredibly important. This is an algebra topic. To find x-intercepts, let y equals 0 and solve for x. To find the y-intercept, let x equals 0 and solve for y. You're only going to have one y-intercept because we have functions. You can only have one value where it occurs, but you could have multiple x-intercepts, or you might have no x-intercepts at all. But this is how we find those. It's, again, something that we did in algebra to find intercepts. So that's going to be one of the first things we do when we're setting up our curve sketching. So let's get started. Use asymptotes, intercepts, and information from the first and second derivatives to graph the following functions. So the first one will be f of x equals 2 divided by x squared minus 4. So this is a rational function. Anytime we have a rational function, we need to consider those vertical asymptotes. Remember that vertical asymptotes can't possibly represent any sort of maximum or minimum value on the graph, but they still need to be included in the sign analysis because we need to consider the behavior between and on each side of the vertical asymptote. So we'll go ahead and talk about the domain. I like to do to talk about the domain before I do anything else in the function. The domain is crucial to the information that we obtain. So we're going to say that x cannot be plus or minus 2. I think that should be pretty clear to everybody. So we'll say x squared cannot be equal to 4. X cannot be equal to plus or minus 2. And you can do that also by factoring using the difference of two squares. So we'll say that we'll start at negative infinity, work our way up to negative 2, and then any value between negative 2 and positive 2 is just fine, and then any value to the right of 2 is also fine. So we're already considering the fact that we're going to have to include plus or minus 2 in our sign analysis, even though we're not getting any crucial information out of those 2 points. We can go ahead and state that we have vertical asymptotes. I'm going to abbreviate those at x equals negative 2 and x equals positive 2. Anytime I find information that's crucially important, I'm going to put a box around it because you're going to find that we have a lot of steps here that we need to complete. So every time I find something that's important, we'll box it so that we can have our attention called back to it very easily when needed. That was talking about the vertical asymptotes. We now need to talk about the horizontal asymptotes, and then we'll talk about x and y intercepts. Okay, so for the horizontal asymptotes, we're going to look at the degrees in the numerator and denominator. Now, in this case, the degree of the numerator is 2. Or I'm sorry, the degree is 0. The numerator itself is 2. Yowza, she's warming up. All right, degree of the denominator is 2. All right, so the degree in the numerator is 0. If you're not sure why, it's because we don't even have a variable in the numerator. So as far as the numerator is concerned, this could just say 2x to the 0 power, and it would be the same. So that's why the degree in the numerator is 0. There's no variable there. The degree in the denominator is 2. If you want to memorize the rule, you can. You can just say, okay, we're looking for the fact we have the degree in the numerator being less than the degree in the denominator, which leads us to y equals 0. The only other thing I would suggest would be that little trick that I showed you back when we were talking about limits at infinity. And what we did for that was we just rewrote the function. So like, let's say we're looking at our f of x. You can rewrite it so that the degree in the numerator, it matches the degree in the denominator. So you just have 2 in the numerator. So you could say, well, if I want these to have the same degree, I need to have an x squared in the numerator. So make it 0x squared. And then when you take the ratio of the lead coefficients, you end up getting 0 over 1, which is still 0. So you get to the same conclusion. Personally, I never remember which one's which if I have to look at these rules and say, okay, which one's less, which one's greater. I only remember the third rule for the degrees being equal. So I always will just take my function, force the degrees to be equal by just writing them with that same power of x, and then I just use that rule number 3 for when the degrees are the same. All right, so I know I have a horizontal asymptote at y equals 0. I put a box around this information. I'm going to gather all my information together at the end, but for right now, I'm done with asymptotes. Now we'll talk about intercepts. So for intercepts, to find the x-intercept, we'll let y be 0, and to find the y-intercept, we'll let x be 0. Now remember, f of x is y. Okay, so to find the x-intercept, let y be 0. You can do this in either order. If we're letting y be 0, we're letting f of x be 0. And then we'll solve. So now we have 0 equals 2 over x squared minus 4. Remember that in order for this rational expression to be equal to 0, only the numerators have to be the same. In this case, we would say that 2 cannot be equal to 0. So you would have no x-intercepts. And again, if you weren't sure about that, you could always multiply both sides by the denominator, and then you'd still end up with 0 equals 2. Well, 0 is not equal to 2. So it can't happen. It's not going to be the case. We don't have any x-intercepts, and actually that's kind of a bummer. When you get this conclusion of no x-intercepts, it's like, oh, okay, fine. It's not the end of the world, but it's really nice just to have a couple points you can put on the graph. Maybe we'll get a y-intercept. Let's see. So to find the y-intercept, we'll let x equal 0. And when we let x be 0, we're looking for f of 0. F of x, f of 0. So this will be 2 divided by 0 squared minus 4. Well, that's 2 divided by negative 4, which is negative a half when we simplify. So we do have a y-intercept in this case. When x is 0, y equals negative a half. So we have a y-intercept at that point. And that's an important conclusion. Put a box around it so we don't lose it for later. You'll notice, like, wait a second, we don't have any more space to write. That's correct. We're going to have to move to the next page. These problems are going to be a little lengthy. I have 3 examples I'm going to go over with you today, and they're lengthy, but they're rewarding. Like I said, don't be afraid of a long problem because we understand exactly what we're supposed to do in each step. We're just putting together things we've already learned. All right, so now go to the next page. I'm going to rewrite my function at the top because I'm going to have to do a little bit of work on it. So I'm going to rewrite f of x equals 2 divided by x squared minus 4. F of x equals 2 divided by x squared minus 4. All right. I'm going to need to do a couple different things now. I'm going to remind you of the directions. First, we said use asymptotes, done, intercepts, done, and information from the first and second derivatives, not done, to graph the function. So we need to now look at the first and second derivatives of this function. So let's focus on the first derivative, get some information, and we'll focus on the second derivative. But it's up to you how you would like to find this derivative. You know that if I have a constant in the numerator, I like to just use the chain rule, so I don't need to use the quotient rule, but that is up to you. So when I take f prime, we have f prime of x is 2 times negative 1 times x squared minus 4 to the negative second. Don't forget to chain on the derivative of the inside function. Now remember, we only need the chain rule here. We did not need the product rule because 2 we don't consider to be a function of x. We just consider it to be a constant multiple in this case. All right, now I'm going to rewrite this because remember, when I'm looking for critical numbers that come out of the first derivative, I like to have the first derivative written as a quotient so that I can look at the numerator and denominator separately. So if I'm going to rewrite this as a quotient, I'm going to multiply here and get negative 2 times 2x, which is negative 4x. And then we'll divide by the quantity x squared minus 4 to the second power. Next, I'm going to look for critical numbers. The critical numbers are when your first derivative either equals 0 or does not exist. So I'm going to find places now. So critical numbers. F prime of x equals 0, or f prime of x does not exist. Okay, so in order for f prime to equal 0, I need the numerator to be equal to 0. And in order for f prime to not exist, I need the denominator to be equal to 0. For the numerator to be equal to 0, I just have x equals 0. Make sure it's in the domain before you put a box around it. Oh, I got rid of this first page, and now I'm going to keep referring back to it. I should keep it out here so we can keep looking at it. We said the domain and only excluded negative and positive 2. So 0 is good for us. Totally fair game. In order for f prime of x to not exist, to have the denominator set equal to 0, I have x squared minus 4 equals 0, and x squared equals positive 4. I'm getting ahead of myself here. X equals plus or minus 2. Now, these values, x equals plus or minus 2, are not critical numbers because they're asymptotes. Vertical asymptotes, not critical numbers. Okay, so they're still important to us in our sign analysis, but they're not critical numbers. Our only critical number is going to be at 0. All right, so let's go ahead and set up the sign analysis with our first derivative. I need to consider all 3 of these values we got out of the first derivative. So I'm going to make my number line. I'm going to start at -2, then go up to 0, and then +2. I'm going to pick test points in each of these 4 intervals, and I'm going to evaluate the first derivative at the test point. So I'm going to choose test point, let's see, f prime of, let's say, -3, f prime of -1, f prime of +1, f prime of 3. And we'll pop these into our calculator and try to determine what the sign of the derivative is in these intervals. Okay, now function. Oh, I missed my window. It was daylight, and when it's daylight, you can see this calculator beautifully in this room. But I missed it. I'm clearly just going to need the emulator. I know I'm going to keep saying that every week until it happens. My first derivative is -4x divided by x squared minus 4 in parentheses. Oh, x squared. How did that happen? -4 in parentheses, quantity squared. Now, I don't care what the graph looks like for the derivative. I only want to know what the sign of my derivative is at all 4 of these values. So I'm going to go to my table, and I'm going to enter -3, -1, +1, +3. And I have values that are positive, positive, negative, negative. So let's see. Positive, positive, negative, and negative. I like for you to tell me what the value is so that I know that you actually checked these and you're not just like, oh, I looked at the graph on my calculator and was able to determine what was happening on that interval. Because that's not what I'm asking you to do. I ask you to show your work. All right, if your first derivative is positive, that means your function's increasing on the interval. Increasing on the interval. If it's negative, we are decreasing on the interval. Now remember, x equals 0 was the only critical number. This is a critical number is a place where we might have relative extrema. Notice that at the critical number, your graph went from increasing to decreasing. That means that you have relative maximum. You hit the top of a hill and you went back down again at 0, f of 0, not f prime, f. That's a point on the graph. All right, so that's going to be important to us. However, we already know what f of 0 is because we already evaluated f of 0 on the previous page. F of 0 is -0.5. So that y-intercept that we have is the maximum value. So this is 0, -0.5. We have that information, and now we, I'm going to put like a cloud around this so we can easily find it later because it's kind of hidden in our sign analysis. Okay, so that's our relative maximum. We can also say something about the behavior of the function on each interval. So we know that the graph is going to be increasing on -∞ to -2, and then again from -2 to 0, and decreasing on the other 2 intervals, so 0 to 2, and then 2 to infinity. Again, these are going to be really important to us as we're sketching our curve. So I'm going to make sure to sort of block off this data so that it really stands out to me when I'm looking for all the important pieces that I need to pull out of this. Now, that was the first derivative. Find the second derivative. And you might be wondering, how am I going to fit all this on here? We're going to do it. We're going to make it fit. Let's see. I'm going to switch my color up here. All right. We found everything we needed with the first derivative. Now we'll find the second. You know what? You'll need to see the first in order to find the second. I can't get everything to display all at once. All right. So here's your first derivative. So f double prime of x, we're going to use the quotient rule for. So f prime is the derivative in the numerator. So that's -4 times g minus f. Don't forget that it's a minus a negative. And then times g prime. G prime needs the chain rule. All divided by g squared. When we square a square, we're taking a power to a power, we multiply the powers, get that fourth power to show up here for us. I'm going to go ahead and cancel out a common factor of x squared minus 4 in all three terms. So this one's going to go to the first power. The second one in the numerator is just going to go all together. And then in the denominator, I'm going to decrease the power down to 3. And then we'll simplify this. All right, so we have -4x squared plus 16. And remember, I can multiply into the parentheses because now the parentheses are only to the first power. If it was still being squared, I can't just multiply into the parentheses like that. But since we're just to the first power, I can do that. Now we have a negative times negative, which is a positive. 4 times 2, which is 8, times 2 is 16. So this will be plus 16x squared divided by x squared minus 4 quantity cubed. It's almost simplified. We'll just combine these like terms here. -4 plus 16 is positive 12 x squared plus 16 divided by x squared minus 4 quantity cubed. There's your second derivative. Now remember, the second derivative is going to give us instances where we have possible points of inflection where the concavity changes on the graph. So we're going to set this numerator equal to 0. If you're already eyeballing the numerator and you're like, wait a second, that doesn't look like it could ever be equal to 0. You're right. And then, of course, the denominator is a whole nother situation there. We already excluded those values. But f double prime of x equals 0 when the numerator equals 0. And that means that we have 12x squared equals -16. Well, that can't be. We can't have a positive number multiplied by an x squared being negative. So it's not going to happen. F double prime of x does not equal 0 when the numerator, or I'm sorry, when the denominator, does not equal 0. I don't know. I keep running things back in my head. And sometimes I think I said something that I actually didn't say and everything was totally fine. Set your denominator equal to 0. And then you just end up with x equals plus or minus 2 again. So these are not points of inflection. Not possible points of inflection. And that's because they are vertical asymptotes. Okay. And we have no possible points of inflection here. So we would say no possible points of inflection anywhere. Like, you're not going to find any. The second derivative cannot possibly be equal to 0. And the second derivative only excludes, and it only could be 0, only could not exist for, we already excluded the domain because they are vertical asymptotes. So we have no possible points of inflection. What we do need to do, though, is set up a sign analysis here with our second derivative using x equals plus or minus 2. So we still need these in the sign analysis. still need in sign analysis always. They're just not points of inflection. I'm totally running out of space, so we might have to put the sign analysis underneath the graph. I know. You would think like, oh, she started on the first page. Now we're on the second page. There's tons of space. I don't know. These problems take up a lot of space. Okay. So I'm going to go through a sign analysis. I'm only going to look at the intervals that are cut off by negative and positive 2, just because I might have the concavity change on each side or in between the vertical asymptotes. So this is what we're trying to do is just determine the concavity of the graph. So we're going to take f double prime and evaluate it. F double prime maybe at 0, and f double prime maybe at 3. All right, I'm going to put this into my calculator. There's not like a whole ton we need to do here, but I need to adjust my numerator. So I'm going to insert some parentheses, and then I'm going to take 12x squared, insert plus 16, divided by, and I'm taking the denominator to the third power. So the numerator is 12x squared plus 16. The denominator is x squared minus 4 to the third power. And we'll go ahead and look at the table and evaluate this at -3, 0, and +3. And we get positive, negative, positive. So that's a result we might have expected. Positive is 0.992, which is greater than 0. At 0, it was -0.25, which was less than 0. You know, I just said greater than and wrote a less than sign. She's losing it. I think I was looking at the -2 that was below this and thinking, oh, -2 is less than 0. All right. This is greater than 0. And then at 3, it was 0.992, which is greater than 0. So for concavity, if this value is greater than 0, it means concave up. If it's less than 0, it's concave down. And then again, it's greater, it means concave up. So you could say that this graph is, let's say, concave up on -infinity to -2 and to infinity. And then it's concave down in the middle, which is from -2 to +2. Okay, so we have all the information. All we need to do now is graph the function. My suggestion to you is to get some sort of straight edge, and I would always graph the asymptotes first, the vertical asymptotes. I'm just going to use this envelope that I see lying on the desk. And I'm going to put the asymptotes on the graph. The asymptotes are crucially important. And then I'm going to put any intercepts I have on the graph. So going through, we're just going to pick out information that we can put on here. Usually I graph the asymptotes first, then I go to the intercepts, which we know we have one that represents the maximum value at 0, -0.5. All right, so our asymptote that lies at x equals -2, it lies on this line. It's a vertical asymptote. I'm going to try to make mine straight. These lines are super faded for me. Just do the best you can. Make them dashed. They don't actually belong to the graph, but they're guiding the behavior of the graph. And we'll make another one at +2. I like to kind of put this here so I can see the axis also. Gives me, I just want it to be parallel to the y-axis. Okay, maybe this one I'll start down here. Okay, so those were the two x-intercepts, and then we have y-intercept. Those were the two vertical asymptotes, and then we have a horizontal asymptote at y equals 0. So let's see. That one is going to be a little bit harder to see, but you're probably going to see it depending on the thickness of your pen or if you put it in a different color, you just want to be able to see it so that it's controlling the behavior of your graph. Now, I want to reiterate, your graph can, if it needs to, cross a horizontal asymptote in the middle. The horizontal asymptote is only guiding the end behavior of the graph. That means that as your graph continues towards negative infinity or positive infinity, it's bound by these horizontal asymptotes. However, you might find that a graph will cross somewhere in the middle. Like it could cross like this and make a curve that runs through. That's a pretty common thing. But don't freak out and think, wait, I thought we couldn't cross an asymptote. You can cross a horizontal asymptote as long as you're not looking at the ends of the graph. You can cross somewhere in the middle. All right, let's put these pieces together. The x or the y-intercept that I have is at 0, -0.5. So I'm just going to do the best I can to plot this on the y-axis at -0.5. And I don't expect to see like a ton of crazy stuff from you regarding plotting points. What I do want to see is that you're just following the behavior of the asymptotes. So if I'm looking at what the graph is doing from negative infinity to -2, I usually try to go from left to right. Well, I know it's going to be concave up from negative infinity to -2. And the other thing that I know is that from negative infinity to -2, the graph is increasing. So if the graph is increasing and it's concave up, remember it has to be concave up cup, so I'm expecting it to have this sort of shape. And if it's going to be increasing, then it needs to be heading towards this asymptote and be concave up. Is this like hand thing weird that I'm doing here? Sorry. But it's going to have some sort of shape like this. The only way it can be increasing and be concave up is if it's sitting above the x-axis. Otherwise, it would have to be like decreasing and concave down if it was down here. It would be like more like that, but it's not. It's increasing concave up. The only way it can do that is up here. So these are going to be, you might have to take some time and really stare at them. But there's only one way that we can be concave up and increasing, and that is if we head up from the horizontal asymptote towards the vertical asymptote. Again, I'm not going to force you to plot a bunch of points here. Sometimes in Calc 1, I might have students give me a point just so they know how sharp this curve is. I'm not super worried about it. I'm more worried about, like, do you understand the behavior of the curve? If it is concave up, it is increasing from left to right, so we're good there. If you'd like, since you already did this end, you could do the other end, or we could just work on the middle. We know that the middle is concave down. Concave down is a frown from -2 to +2. If it's a frown, and we know that the maximum is at the y-intercept, there's only one thing that it can be doing, and it has to be doing something like this, where it approaches the vertical asymptotes on both sides as it heads downwards and it's concave down. That is the only way for it to be concave down and be increasing from -2 to 0. That's another thing you could look at. I mean, we look at the max, but it's increasing from -2 to 0 and decreasing on 0 to 2. So here you have increasing up to 0 and then decreasing up towards 2. And the last part of this is just what's happening as we are to the right of 2. So I know that we are concave up from 2 to infinity. Another thing that I know is that from 2 to infinity, we're decreasing. Same idea. The only way in this case that I could be concave down and decrease, wait, no, concave up. Oh, I was like, wait a second, this doesn't look right. Concave up and decreasing. I'm using these two pieces of information, decreasing, concave up from 2 to infinity. I must be here. Decreasing, concave upwards. So I know it's only half of the cup, but it's still a cup shape. It's not a frown. If this had been concave down instead of up, and you were decreasing in this interval, actually, I don't know how you could have done that. Pretty much only one way of doing that. I don't know. You could have been increasing concave down and been down here. but you could not have been doing either of the other two things. Wouldn't make sense with these asymptotes. All right, when you're done, notice how I first of all have these little arrows on my graph indicating the behavior of the graph, but you can always plug this in your calculator just to check it, make sure that this makes sense. I'm going to go to my y equals, and my original function was 2 over x squared minus 4. I know, it's like it's getting harder and harder to see. Okay, 2 over x squared minus 4. It's like there's no, I wonder if I turn this on. Oh, kind of. Okay, we'll just do that. 2 over x squared minus 4. All right, I'm going to zoom 6. There it is. If you want it to look exactly like the one on your page, you're going to have a hard time doing that because of the rectangular nature of the screen, but you can zoom 5 and you'll get it to be a much closer picture. And again, I didn't have you graph a bunch of points. If I had, we would have probably figured out that if we let x be 1, y is probably like -1. See what happens when we let x be 1. No, it's only -2/3. So that's why your graph looks a little bit more steep probably if you didn't plot some values, because really this point should be -2/3, which is right up here. So your graph should open a little bit wider, but I'm not too picky about that. I just want to make sure, like, do you have the general shape of the graph? That's what I'm looking for. Terrific. All right. Next. I used to teach a synchronous class from this room. I had all these things I would do as it got dark outside. And one of the things that I would do is I would pull this light over. Let me just do that real quick. This is what happens when I record on this transition hour. That's better. Okay, now, do you know what that clanking was? My base metals. Okay. Anyway, much better. Next. Hopefully that gave you a chance to catch up a little bit. Number 2. This is the function. I'm going to start it up a little bit higher just because we're going to need a lot of space to do this. Everything's going on this one page. X times the square root of 1 minus x. If you'd like, since you know that at some point you're going to be taking the derivative of the function, I would recommend writing it as x times 1 minus x to the half, just so that we have that ready for when we need it. Now, it's a square root function, and as you know, that's a huge issue for us domain-wise. So we should probably go ahead and list the domain. I need for whatever is under the radical to be greater than or equal to 0. So 1 minus x has to be greater than or equal to 0. In this case, do this however you'd like. I'm going to go ahead and add x to both sides. And that means x has to be less than or equal to 1. That means my domain is actually going to be negative infinity. Oh, it's positive 1. Sorry, not negative 1. Up 1. And we're going to put a bracket on it because we can include that endpoint. It's not going to be a huge issue for us here, but we will see. So that's the domain of our function. The first thing we do is find the domain, then we talk about any possible asymptotes, and we talk about intercepts. So if we're talking about asymptotes, that'll be the second thing we look at. Well, remember we get vertical asymptotes when we're looking at a rational function and we're dividing by 0. So for vertical asymptotes, we don't have a radical function. And I am not going to be dividing by 0 at all here, so we're going to say none. And then for horizontal asymptotes, again, I'm looking for a rational function, and I'm comparing the degrees in the numerator and denominator. Your radical function doesn't have asymptotes. It's not written as a rational radical function, so you're not going to have asymptotes. It's that you get off easy there. Maybe. Sometimes asymptotes are nice because, again, they guide the behavior of your graph. All right, so we don't have that, but that's okay. Next, we will talk about intercepts. I'm just going to put all this algebra stuff here at the top. I'm just anticipating running out of space. I'm writing small. You have the other side of your notes, though, to use. So if I were you, I would just go whoop, and then just write on the other side. If you run out of space, you can see it left to right. I don't know how you're keeping your notes. If you're keeping them in a binder, that'd be a good idea. All right, so for the intercepts, to find the x-intercept, let y equal 0. And when you let y equal 0, you're letting f of x be 0. So we're saying 0 is x times the square root of 1 minus x. So in this case, when we're letting y be 0, we can go ahead and solve for what value x would have to be for our intercept here. So if we have x times the square root of 1 minus x, we'll have x equals 0. We'll talk about that in a second. Or we have the square root of 1 minus x equals 0. Square both sides and you get 1 minus x equals 0 and x equals 1. Okay, now 1 is not a problem. 1 is in the domain of your function. So we can go ahead and say that we have an intercept at 1, 0, because remember to find the x-intercept, let y be 0. But remember that this was the endpoint of your domain. You can include any values of x in this function from -infinity all the way up to 1. So 1's okay. What about 0, though? In this case, we would say that 0 is still okay because it's not -1, it's +1. So we could also use 0, 0. Now, for the y-intercept, we let x be 0. And if we let x be 0, again, we're just looking at f of 0, which would be 0 times the square root of 1 minus 0, which is 0. Well, we already found that. So the y-intercept is also an x-intercept. It's not that interesting, but it's still a conclusion. It's still a point on the graph. So we have 2 points that we'll at least be able to graph on our graph. So that's helpful. Okay, so we found the asymptotes, we found the intercepts. Now we can get going on our first and second derivatives. So let's go ahead and find f prime. F prime in this case is going to use the product rule and the chain rule, because remember, this is not just x to the 1/2, it's 1 minus x to the 1/2. The derivative of the inside function is -1. So let's go ahead and take f prime. F prime of x is, let's see, I'm calling it f prime, and then I'm of course calling this f prime. I know, old habits die hard. F prime g. And then the question is, which notation do we want to keep? I'll keep the rational exponent for now. And then plus f g prime. So g prime is going to be 1/2 times 1 minus x to the -1/2, multiply it by the derivative of the inside function. Now, we're in a situation here where we have -1/2. That's going to move into the denominator. So we're going to simplify this as one fraction. Right now, I can just say that I have, I totally want to write this as a radical, so I might write it as a radical. I think it's easier to use algebra on radicals. All right, so I'm going to rewrite this 1 minus x to the 1/2 as a radical. And then I'm going to simplify this term. So I have -x times 1/2. So it's -x over 2. So I'm just going to write minus and then x divided by twice the square root of 1 minus x. And then we can write this as one fraction so that we can look for critical numbers, looking at where the numerator is equal to 0 and where the denominator doesn't exist. So to write this as one fraction, I'm going to multiply the first term by this denominator 2 times the square root of 1 minus x. So remember, I'm not changing anything. I'm just rewriting it so that we can combine these two. So I currently have square root of 1 minus x. I'm going to multiply it in the numerator and denominator by twice the square root of 1 minus x over itself. Haven't changed it. We're just rewriting it. And then we'll simplify. If you want to write this all as one fraction, go ahead. And then we can go ahead. Don't cancel these out. You did that for a reason. The square root of 1 minus x times itself is 1 minus x. So the first term gives you twice 1 minus x. The second term still just has minus x. Your denominator now stays the same. If this is one of those spots where the algebra is sticky and you need to pause it and go back, please do so. 2 minus 2x minus x is 2 minus 3x over twice the square root of 1 minus x. I'm going to just call this out again as f prime. So we're looking for places where the first derivative either equals 0 or does not exist. F prime of x equals 0 when 2 minus 3x equals 0. And that means when 3x equals 2 and x equals 2/3. And then you're going to ask yourself every time with these, you're going to say, wait a second, is this in the domain? Yes, 2/3 is less than 1. This is in the domain. This is going to be a critical number. Put a box around it. As far as the denominator is concerned, you're taking the denominator and setting it equal to 0, and that is where f prime of x does not exist. This is going to happen. You can divide both sides by 2, square both sides. 1 minus x equals 0, which means x equals 1. Now, x equals 1 is an endpoint of the domain. Remember that you can't have a maximum or a minimum value if you can't create a neighborhood around that point. Because it's an endpoint of the domain, it's not actually going to be a critical number for us. So I'm going to go ahead and say that this is an endpoint. So it means not a critical number. It's still going to go in our sign analysis. It has to. It's the last value we're using. But we're not going to test the value there. I mean, and plus we already know, because I think, we already found that the value at x equals 1 is 0. So we have a point there. It's just not going to be any sort of extreme value for us. Local extreme, I should say. All right, f double prime, we're ready for it. Oh, wait, I didn't do the sign analysis. Okay. Sign analysis. There's not a lot to do here because we only have one critical number and we don't have any sort of any like asymptotes or anything we need to include. So I just need to think about what's happening to the left and the right of 2/3. Remember that your right endpoint is 1 and your left endpoint is negative infinity. So you just need to pick a test value somewhere in this region. So I would say probably you could test f prime of 0. Why not? And then maybe test, don't pick 1. You need to pick a value that's somewhere between 2/3 and 1. You just pick decimal. If you know 2/3 is like 0.67-ish, then I would say maybe test something like 0.7 or 0.8, something like that. Just something that's in between 2/3 and 1. Okay. So we're going to look at the first derivative evaluated at these numbers. Light trick here. So I'm going to enter the first derivative, which is 2 minus 3x in the numerator. I'm going to put parentheses around that, divided by 2 times the square root of 1 minus x in the denominator. That's my first derivative. I'm going to evaluate it at these two critical numbers. So I'm going to go to my table. The two numbers in question are 0, which is actually already there, and 0.8. So at 0, we get 1. And at 0.8, we get negative 0.447. So 1, of course, is greater than 0. Negative 0.447 is less than 0. That tells us something about the behavior of our function at the on each side of this critical point. So we would say that the function is increasing on the first interval because the first derivative is positive, and decreasing on the second interval because the first derivative is negative at that test point. So we can go ahead now and say something about 2/3 representing a relative maximum. At 2/3, f of 2/3. And we'll get f of 2/3 in a minute. Right now, I would say leave it. All right, so that's our sign analysis. Let's go ahead and start working on the second derivative. I'm trying to conserve space, so I'm going to start it over here, but you do whatever works best for you. Let's see. Second derivative f double prime. Oh, you know, this always ends up looking gray. Not the best choice. F double prime. All right, so I'm going back to my first derivative. If you want to rewrite your first derivative now, again, with a rational exponent, you might want to do that. We'll say it's 2 minus 3x divided by 2 times 1 minus x to the 1/2 power. And that's your f prime. So always just rewrite it for whatever it is that you need to do with that expression. F double prime is, let's see, f prime g minus f g prime. So 2 times half is just going to be 1. 1 minus x to the negative half, multiply that by the derivative of the inside function, which is -1. And now when I take g squared in the denominator, I'm going to take 2 squared, which is 4. I might as well just square it right now. I can square these two factors separately. So 2 squared is 4, and then the square of the square root of 1 minus x is just 1 minus x. When you square root, you just get whatever's left underneath the radical by itself. All right, let's simplify this bear. Okay, I'm going to get -6 times. Kind of want to switch this back to a radical now. 1 minus the square root of x. I've got a minus and a minus. I'm going to call that a plus, and then 2 minus 3x divided by the square root of 1 minus x, because it's to the -1/2 power. And then we'll divide it out again. And it is up to you how you want to do this. I'm going to go through and multiply my fraction by the LCD, which in this case is the square root of 1 minus x. So I'm right here. Now I'm going to multiply every term by the square root of 1 minus x so that I can get rid of the complex fraction. And we'll simplify the second derivative. So the square root of 1 minus x times itself is just 1 minus x. And then I have these two canceling, so that only leaves me with 2 minus 3x. And then in the denominator, I have 4 times 1 minus x to the 3/2, or you can just leave it separated if you want. This notation is absolutely fine. It's up to you. Let's go ahead and simplify the numerator. So we have -6, and +2, which is -4. And then positive 6x minus 3x, all divided by 4 times. I'm even going to split mine up again, up to you. I don't know. Sometimes it's easier to see when it's split up. Okay. And then we'll take our possible points of inflection. We're going to take f double prime of x and set it equal to 0. So you're going to take the numerator and set it equal to 0. And you'll get x equals 4/3. Is 4/3 in your domain? Three-thirds is 1. 4/3 is more than 1. So if you find a value that's outside of your domain, I'm glad you found it. Show me that you looked for it at least, but say that it's not in the domain of f. Okay, and then the other thing we're going to do is look at values that make the denominator equal to 0. So you're going to say f double prime of x does not exist. Oh, now I wish I would have left it in this notation. It doesn't exist when we have 1 minus x to the 3/2 equals 0. Take both sides to the 2/3. I know, technically, I think you probably don't really need to show this step. And then equals 0 to the 2/3. And then you end up with 1 minus x equals 0 and x equals 1. Oh, gosh, I'm sorry. So far down here. I lost you all. Lost everybody. Okay. All right. So x equals 1 being a point of inflection is not going to make any sense because that's the end point. A point of inflection means the concavity changes from up to down or vice versa at a particular value. The concavity can't possibly change at the end point. So we would say no possible points of inflection. So we cannot have this be, this is not a POI. Okay, so we have no possible points of inflection. We ended up coming up with this relative maximum value, though, at 2/3 f of 2/3. That's going to be important to us, and we can say something about the concavity. Oh, goodness, you know what I forgot to do was state intervals where the function's increasing or decreasing. I mean, I put it here, but I didn't actually write it out. So let's start to make some conclusions here. As far as f prime was concerned, I had that the function was increasing on the interval from -∞ to 2/3 and decreasing on the interval from 2/3 to 1. So it doesn't happen for very long. And I know 1, I should have probably even left it open just because you can't really be decreasing at an endpoint. All right, so we have that, and then we have the relative max. Let's go ahead and find that corresponding y value, f of 2/3. So f of 2/3 is equal to, well, your function is x times the square root of 1 minus x. So it's going to be 2/3 times the square root of 1 minus 2/3. And we'll get a value here for this. 2/3 times the square root of 1 minus 2/3 is 1/3. Let's be real here. We're going to be graphing this value. So if we get a decimal approximation, that's probably just fine. So I'm going to put in 2/3. Oh, don't have the light situation. Okay. 2/3 times, and if you even want to put the whole thing in, that's fine. 1 minus 2/3 under the radical. 2/3 times 1 minus 2/3 is approximately 0.385-ish. So your relative max is at the point 2/3 at approximately 0.385. So that's an important conclusion, an important piece of information, and a point that we'll put on the graph. Okay, let's see. Concavity, we need to make some conclusions on. We did not even do a sign analysis. Oh. You know why we didn't do a sign analysis? Because we didn't have any possible points of inflection, but we technically still need one. So our sign analysis is only just going to talk about what's happening on the entire domain of the function, from negative infinity to positive 1. And if you're like, okay, but I thought you said there were no POI, possible points of inflection, you're right. There are no possible points of inflection. So that means the concavity is going to be the same on its entire domain. So you just need to pick a test point somewhere in the domain to talk about concavity. So like, let's talk about what happens at 0. We're just going to pick a test point in the domain. And we'll take f double prime of 0. But usually we don't actually plot that. So I don't want this to look confusing. So I'm just going to not put this point on there like it exists. It's not a point of inflection. This is just a test value. Test value in the interval. So let's test it. F double prime at 0. Is this an easy one to check? Okay. So when x is 0, I'm looking at f double prime. We just have to evaluate 1. You really want to put this whole thing in your calculator. If x is 0, the numerator is going to be negative. Technically -4. Divided by, and then if x is 0, we've got a 1 and a 1. This will be a positive 4. -1 is less than 0. So that means we're going to be concave down on the entire domain. Is there anything else we missed? Let's see. We did a sign analysis twice. We got relative maxima information, increasing, decreasing. We have an intercept. All right, let's go ahead and start to plot this. I know you're like, oh, this is taking forever. I know it is. Terrific. Let's see. We're only going to include x values from negative infinity up to 1. We have points on the graph at 0, 0. And 1, 0. We have no asymptotes, but we can at least plot those 2 points, 0, 0, and 1, 0. So there's something happening in between here. What's happening in between these 2 points is, because you know something's happening, it's the relative maximum that's occurring here at 2/3 and 0.385. So at 2/3, 0.385, you're just going to have to eyeball it. It's about right there. No, it's hard to see. This is the maximum. We're going to plot through that point. Now, if you know this is maximum, you know that the graph has to be going down on both sides. Your question is just like, what exactly is it doing? How quickly is it doing it? You're going to have to do your best. It's concave down on the entire domain. So you know the whole domain's around. We know that the graph is going to be increasing up to 2/3 and decreasing down to 1. And 1 is the last point that we're going to graph. So this value at 1, 0 is an endpoint. So we know if this is a max in between, there aren't any other values in between. You're going to connect these with a little hump. And then you know from negative infinity all the way up to 2/3, the function's increasing. So it has to be coming up from, I don't know, from negative infinity. Now, I'm guessing here, it's probably actually even supposed to be more narrow. I sort of made it pop out a little bit more. but this is what the graph is doing. The arrows down here to indicate that this behavior continues. It's concave down on its entire domain. It's increasing up to the relative max, and then it starts to decrease up until you get to that final value. We'll put this in our calculators and check to make sure that our graph matches, but I know it's like not that interesting of a graph, but it kind of is because there's these little tiny things happening. I'm going to zoom 6. There it is. So now if you were to zoom in a little bit, you can see that hump where you have that maximum value, but that's the relative max that we found. Not bad, huh? So a lot of the trick here is just making sure that you're actually getting all the information that you need. It's so easy to skip over something. And then, I mean, you saw me do it and then like, wait, hold on a second, let's go back to that. You're just constantly like making a check of like, okay, what do I need to do? What am I looking for? And even though you've already found the first derivative, it's still like, okay, well, what do I need to do with that? Like I need to do a sign analysis, and then what? I need to make conclusions based off the sign analysis. And you're just kind of running your way through. Let's do one more. Just do this. All right, excellent. See what I have in store for you for one more. It's another rational function. F of x equals, rational functions are pretty popular with curve sketching just because they can do all kinds of different things. They're very interesting. Okay, 4x divided by 1 plus x squared. And you might be looking at this and like, wait, didn't we just sketch that? Well, no. The one that we sketched was 2 divided by x squared minus 4. And I know they're similar, but not really, because in this case, the numerator has a variable in it, where in the first example, it did not. And the biggest difference is that this denominator has a plus sign between the two terms. Unlike that one, where we really had a situation where we had some issues with the domain. Now, we're going to go ahead and list out the domain here, but there's nothing really to say about it. And that's because x squared cannot be equal to -1. So we can say that the domain in this case is all real numbers. There are no values to exclude. Just because there are variables in the denominator doesn't mean that you're going to have issues with the domain. In this case, you cannot possibly find a value of x that's going to make the denominator 0. It can't happen. So go ahead and list out the domain. And once you do that, the natural progression is to start talking about the asymptotes. If your domain from -infinity to +infinity, then as far as the vertical asymptotes are concerned, you don't have any. And it is an important conclusion, so I'll put a box around it. No vertical asymptotes. They're not on the graph. For your horizontal asymptotes, these the degree in the numerator is less than the degree in the denominator. If you would like, you can use my little trick, and you can say 0x squared plus 4x divided by x squared plus 1. Well, now the degrees are the same, and you can conclude that the horizontal asymptote is the ratio of the lead coefficients, which is y equals 0. Okay, so this is your horizontal asymptote. I don't know why I put that so far. I was going to say something else about it. Maybe I was going to spell it out. I'm not sure. But horizontal asymptote is y equals 0. Okay, so this is all the preliminary information for algebra except for the intercepts. So let's go ahead and list the intercepts. To find the x-intercept, let y be 0. So to find the x-intercept, we're going to let y be 0. That means 0 is 4x over 1 plus x squared, which means that 4x is 0 and x is 0. That gives you a point on the graph. Not the most interesting point in the world, but a point nonetheless. Then we'll find the y-intercept. You find the y-intercept by letting x be 0. So that's f of 0. which is 0, over 1 plus 0 squared, which is 0. So I don't know why I'm rolling my eyes at that. I mean, it's still a conclusion. It's just that we already found that conclusion. So, okay, I guess put a box around it. You know that there's at least one point on the graph at 0, 0 that you can put on there. The rest of it we're going to have to ascertain from the first and second derivatives. So without further ado, let's find f prime. Prime of x. F prime g minus f g prime. Well, at least it's not a quantity that's being squared. All divided by g squared. I mean, it will be with the second derivative, but I'm trying to look on the bright side. So you're going to have 4 plus 4x squared minus 8x squared divided by your denominator squared is 4 minus 4x squared divided by your denominator squared. This is f prime. I'm going to call it out so that we can easily see it when we take f double prime. All right, now we're going to look for critical numbers. So we're going to look for values where f prime of x equals 0. And that's going to be where 4 minus 4x squared equals 0. I'm just going to add 4x squared to both sides, I guess. So we'll have 4x squared equals 4, and x squared equals 1. That means x equals plus or minus 1 will be critical numbers. For the denominator, f prime of x does not exist. You're not going to have any values for that. So I'm just going to say none. You cannot possibly get 0 in the denominator, which is the same reason we had no vertical asymptotes. Okay. So these are your critical numbers. X equals plus or minus 1. This is where we're expecting that we're probably going to have some relative extrema. In order to determine that, let's go ahead and set up a sign analysis. At -1 and +1. We don't have any vertical asymptotes that we need to put into the sign analysis, so we just need to worry about these two values. I'm going to test f prime of -2, f prime of 0, and f prime of +2. And we'll test all of these in the calculator. Again, up to you. You can do it by hand if you want, if you feel like it's a pretty straightforward function. I'm going to go ahead and enter mine as 4 minus 4x squared divided by 1 plus x squared quantity squared. And then we will go to our table. I'm going to enter -2, 0, and +2. Now, I'm just going to write negative, positive, or negative, depending on what it is. But like I said, on your exam, I want to see the values, so I know you actually plugged them in and you knew what you were doing. So f prime of -2 is less than 0, f prime of 0 is greater than 0, and f prime of 2 is less than 0. So we're going down, up, down. That means that both of these critical numbers yield relative extrema. I kind of like this light on now. So we must have a relative minimum at -1 and f of -1. And a relative maximum, so you're going up and then back down again at 1 and f of 1. If you'd like, go ahead and use those in your calculator now. You're going to have to change the function in a minute anyway to put your second derivative in, so you might as well just get values here. Are these supposed to be exact? Yes, they are, so I'm not like super worried about it. So I'm looking for f of negative and positive 1. The function is the original function, which is 4x divided by 1 plus x squared. Or you can just evaluate it by hand, up to you. Go to your table, get some values for -1 and +1. It's -2 and +2, respectively. -2 and +2. Okay, so this is a really super important conclusion. I'm going to put a thought around it. Now, if you want to go ahead and make a statement about where your graph is increasing or decreasing, now would be a good time to do that. But if you kind of feel like you can look at the sign analysis to state that, that's also okay. My big thing is I just want to see your work. So if you're graphing and you're like eyeballing your sign analysis, it's fine because it's there. So you kind of know, all right, I'm increasing or decreasing. But now that I've made this whole hoopla about talking about it, we'll say that your function is increasing on -1 to 1 and decreasing on -infinity to -1 and +1 to +infinity. Oh, sorry, I'm doing that again. Wonderful. So second derivative time. F double prime. You can see your F prime is up here in this box. F double prime of x is F prime g, so -8x times your denominator minus your whole function f times g prime, which needs the chain rule. Twice 1 plus x squared to the first power and multiply it by 2x. Divide by g squared. And then we'll simplify. Before you start multiplying everything in, please cancel out your common factor of 1 plus x squared to the first power in all three parts of your second derivative. And now you can multiply the 8x into the parentheses. Then we'll simplify again. So let's see, we have -8x, and then minus 8x cubed. And then I've got this 2 here times a 2, so I've got a 4x that I'm going to multiply in. Those make 4x, I'm going to multiply it into these parentheses. So I'm going to have minus 16x, and then plus, so minus a negative 16x cubed, divided by the denominator, 1 plus x squared to the third power. Then we'll simplify it one more time. F double prime of x equals a negative 24x. Or if you want to do this in descending order, you can write this as positive 8x cubed minus 24x divided by 1 plus x squared, quantity cubed. And now we'll look for possible points of inflection. It looks like we're going to get f double prime of x equals 0. I like to start with equals 0. Technically, you could start with does not exist, but I like to start with equals 0. That's going to be when the numerator equals 0. I'm going to go ahead and factor it just because it's one less thing I have to write. I'm going to take out an 8x. That leaves me with x squared minus 3 equals 0. So that means either x equals 0 or x squared equals 3. If x squared is 3, that means x equals plus or minus the square root of 3, which is about plus or minus 1.7 something. What is the square root of 3? Square root of 3 is about 1.73. Okay. Now, again, we need to check to make sure that these are in our domain, but our domain was all real numbers. So of course they're in our domain in this particular instance. So you actually have 1, 2, 3 possible points of inflection. We'll know their actual points of inflection if the concavity changes there. Now, as far as our denominator, f double prime of x does not exist. Well, that's going to be another none situation because 1 plus x squared cannot be equal to 0. So, all right, we have possible points of inflection. Here and here, these are possible points of inflection. So if the concavity changes at these points, we'll upgrade them to points of inflection, and then we'll list them as ordered pairs on the graph, or list them as ordered pairs on our page. I need to do a sign analysis. We're going to do this on the bottom because that is the only place I really have space to do this. So let's go ahead. We'll include the smallest one at negative square root 3, the largest one at the square root of 3, and in the middle we have 0. And then we'll test some values between here. That's kind of why it's nice to have this decimal approximation that helps you find a test value. So maybe I'll test f double prime of, it's got to be less than negative 1.73. So we'll go f double prime of negative 2, f double prime of negative 1, positive 1, and positive 2. Okay. Ready for our sign analysis? We got to put the second derivative in. All right. Second derivative is parentheses 8x cubed minus 24x divided by 1 plus x squared quantity cubed. Go to my table now. We'll look at these 4 values, negative 2, negative 1, positive 1, positive 2. Now we can see what's happening with our concavity. We're going negative, positive, negative, positive. Negative, positive, negative, positive. Now we can make some conclusions about concavity. Concave down, concave, concave down, concave up. All right. Again, if you want to write these out in intervals, that's absolutely fine. I don't know. I kind of think we need to just write out the points of inflection now that we know they are points of inflection. So on your exam, when you have points of inflection, I'm going to ask you to write them as ordered pairs. So we know that one of them, because the concavity changed in all 3 of these instances. So we know that all 3 of these values are going to represent points of inflection. So we can say we have points of inflection. And they're going to occur at negative square root of 3, f of negative square root of 3, 0, f of 0, which we already know actually is 0, 0, because we found that point earlier. The y value at 0 is 0. And the square root of 3 and f of the square root of 3. And when I have you list out these points of inflection, I would like for them to be exact values. So let's go ahead and find these as exact values. We might run out of space here. I'm going to go to my left side of the page, which is why I leave these single-sided. I just need to know what is f of plus or minus the square root of 3. So I'm just going to find that separately. So negative square root 3 f of negative square root 3. And positive square root 3 f positive square root 3. Okay, so my function, my original function was f of x is 4x divided by 1 plus x squared. So if I'm trying to find the function value here, in the first instance, I'm looking at, here, I'm just going to write this on the below. Okay, I'm going to write f of negative square root 3 is equal to 4 times negative square root 3 divided by 1 plus negative square root 3 squared. This is negative 4 times the square root of 3 divided by 1 plus, well, negative root 3 multiplied by itself is just positive 3. And you end up with just negative square root 3. Isn't that crazy? If you evaluated the positive square root of 3, you'd get something similar. The only difference is that the numerator would be positive instead of negative. So you get 4 square root 3, and then 1 plus 3. 4 root 3 over 4 is the square root of 3. Technically, you should have learned how to do this in your prereq. I just want to make sure everyone understands how to do this. So my f of negative root 3 is negative root 3. My f of root 3 is root 3. So I'm going to go ahead and list these as my points of inflection. So this is going to be negative root 3, negative root 3, and positive root 3, positive root 3. So those are the points of inflection. We have a relative max. We have a relative min. We've got so much going on here. Let's go ahead and plot this curve. I feel like I just want to say one more thing. Concave down on negative infinity to negative root 3, and then 0 to positive root 3, and then concave up on negative root 3 to 0 and root 3 to infinity. There, I feel better now. Everything's listed. Every possible thing is listed. Here's the conclusion from your sign analysis from the second derivative. Here's your conclusion from the sign analysis with the first derivative. Everything is on here, even though it's crazy. It's kind of organized. All right, let's go ahead and plot some points. We only have 1 point, and that point so far is, well, we have a couple points of the derivatives, but the only point we have from our algebra is 0, 0. So we know that this graph crosses the origin. I think it's going to be most helpful to do this in order. I like to plot the mins and maxes first and then just sort of work around those. So we know that we have a relative minimum value at -1, -2, which is right here. -1, -2. And we have a relative maximum value at +1, +2. So that's going to go up to here. And for the rest of this, we're just going to look at where the function's increasing or decreasing and the concavity. Oh, I almost forgot. One really important thing I forgot to put on here is the horizontal asymptote at y equals 0. That would have been a terrible thing to omit. Terrible. See what I mean? You just kind of go through and you're like, wait, what do I need? I usually put the asymptotes on first, but I was so focused on the lack of vertical asymptotes that I wasn't even thinking about the horizontal ones. There we go. So like I said, you can cross a horizontal asymptote in the middle, but at the ends, we cannot be crossing it. Let's see. Now, I know that from negative infinity to negative square root 3, which is like negative 1.73-ish, the concavity is going to be down. Now, if you want to plot the points of inflection, you might find that to be most useful since you know the concavity is changing on both sides of them. Now, we have these points of inflection as exact values. If you wanted to write them as approximate, I mean, we already know that plus or minus the square root of 3 is about 1.73. This is going to be negative 1.73, negative 1.73. And the other one will be positive 1.73, positive 1.73. And then, of course, 0, 0 is going to represent a point of inflection. So I'm going to put these on the graph. I'm going to eyeball it. It's really hard to see these. So negative 1.73 is about here-ish, and negative 1.73 is about here-ish. Do the best you can. This is going to be a point of inflection. And then same idea here, 1.73, about 1.73, the best you can. It's a point of inflection. The points of inflection really are helpful when you graph them. It's just more points you can see on the graph. And 0, 0, we already have graphed. We already graphed the max and mins. And all we have left to do is just use the concavity and the increasing, decreasing information that we have to put this graph together. But we have a lot of information. All right. From negative infinity to your first point of inflection, which is right here, it's concave down. And we know that it has to be approaching the asymptote. So it cannot possibly be concave down and coming from above the asymptote because we can't be crossing it at the ends. Another thing to consider is that the graph is decreasing from negative infinity to negative 1. So the graph is decreasing concave down. The only way for it to do this and approach the asymptote as x gets very, very small is to do this. And again, do the best you can. This is concave down and decreasing. Now you're going to be concave up and still decreasing, because remember we're decreasing up to negative 1 in this little teeny tiny interval. So you're going to be concave up. So do the best you can. I know it's going to be hard to make this look concave up, but try not to make it look sharp like that. I'm just mostly making mine a little bit exaggerated so that you can kind of see what's happening, but it's concave up, decreasing. Then we go to, let's see, where was it? Concave up. It's still going to be concave up, but now it's going to be increasing between negative and positive 1. So we're going to be increasing here and concave up for the up to 0, increasing all the way up to 1. So concave up, cut, concave down, frown. Okay, so you can see how the concavity changed from up to down at 0. Now my concavity is going to change again at this point of inflection that we haven't hit yet, but we start to decrease because now we're getting past 1. So now I'm going to be decreasing concave down. And then after that, concave up from this point of inflection as I approach the asymptote, as I continue now to decrease. So concave up, kind of like that. I know it's a tricky one just because there are a lot of little things that are happening in one space. It's like, wait, this is happening, that's happening. All these different things are changing at these different values. Put in our calculator so that we can check our graph, make sure it looks good. Of course it does. 4x divided by 1 plus x squared. All right, moment of truth. Oh, I was the only one that to participate in the moment of truth. There it is. Isn't it beautiful though when you get to see the calculator's version next to your version of the graph? You're like, oh wow, I did such a good job. I mean, obviously, I like I said, I exaggerated this. It should be smooth, but I really just kind of wanted to show that shift in the concavity. But sometimes it's really hard to see that concavity change. But that's curve sketching. So hopefully it was also a really good derivative review for you, a really good review of 4.1 and 4.2. But that's the thing. You can't go through 4.3 without really getting to know 4.1 and 4.2. So if you were still kind of struggling with that, again, it's not going anywhere. We're going to be applying all of these rules to functions in chapter 5 with logarithms and exponentials. So none of these are going anywhere. You're going to keep seeing them over and over again. So if you're like, oh my gosh, I hate curve sketching. Well, I hate to tell you, you're going to have to keep doing this. So you should learn to love it. It's really good for you. It's so good for you. Is that is it, right? Yeah. Okay. That's it. So good luck with curve sketching. I really recommend doing these on paper, pencil, because I know that you have WebAssign homework and I don't want you to just put the graph into your calculator and then just look at it on WebAssign. So it's possible that I might assign some homework by hand for these. I'm going to see. But I'm going to also just try to give you problems that maybe rely a little bit less on the numbers and just more of you using the data to graph it. But we can talk about this in class. Please email me if you have any questions. Let me know. Stick around for the office hour and go into the tutoring center and get help when you need it. It's free. That's all I have to say. Have a wonderful rest of your day, and I'll see you, as always, on a Tuesday.